Hey everyone, here's your Sioux Falls physics teachers, and today we begin looking at parallel circuits. 3 resistors are given. They're connected in a parallel circuit with 12 volts. We need to draw a circuit diagram, calculate the equivalent resistance and total current in the circuit. We'll begin with the circuit diagram. Notice again that when we include a resistor, the resistor is given by kind of a little jaggedy line. If all 3 are in parallel, then we would draw them all on separate lines of the circuit, and then that eventually needs to connect back to the battery. And at this point we can do our labels. The battery is 12 volts, and our resistors are 33, 45, and 86 ohms. Now we're ready to calculate the equivalent resistance. And remember that for resistors in parallel, the resistance actually goes down. So we calculate that by adding the inverses. So 33 ohms, 45 ohms, and 86 ohms will all be added as their inverses. And the final answer, again remembering to take the inverse as your final step, turns out to be 15.6 ohms as the equivalent resistance for the entire circuit. Next we need to calculate the total current, and for that we'll go to our equation V equals IR. And remember that when we look at this equation, we can apply it in this case to the entire amounts for the circuit. So we'll put the little substep for equivalent there. That reminds us that we want to use total amounts. Our total voltage is 12. We'll be finding the total current, and our total resistance, just calculated at 15.6 ohms, gives us an equivalent current of 0.77 amps as our total. Hey everyone, here's your Sioux Falls physics teachers looking a little more today at parallel circuits. This time we have 2 resistors, both of 100 ohms and attached to 120 volts. We have a nice little list of things to find, including a circuit diagram, total current, and amounts across each individual resistor. So we'll begin with the circuit diagram, and again for parallel circuits, we simply want to make sure to draw 2 individual pathways to the battery. And in this case, our battery or our power supply is 120 volts. Our 2 resistors are 100 ohms each. Now, first it says to determine the total current. We will not be able to do that without first determining the equivalent resistance. Again, for parallel, we find that amount by adding the inverses. So in this case, 100 ohms, and the second resistor is also identical, so also 100 ohms. And you hopefully should be familiar enough with this pattern to know right away that if they are equal resistance values, when I do the math, I should get a value that is 1/2 of our original amount. So 50 ohms then is the total resistance of the 2 acting together in the circuit. Now that will allow us to first determine the total current, which is our first unknown on the list. Again, we'll be using Ohm's law, and we want to start by applying that to the entire circuit. So 120 volts. The current is our unknown, and 50 ohms as our resistance gets us a equivalent current, or a total amount for the circuit, of 2.4 amps. Now at this point it asks for a couple of things about each resistor individually. We want to know the current through each resistor and the voltage across each resistor. We'll see later that if we need to, in more complicated situations, there are ways to calculate these things. But in this case, since they have the same resistance, there are a couple of pretty easy patterns that we can use to determine these things really without any extra calculation. Let's start with the current through each resistor. We just determined that the equivalent current is 2.4 amps. So if I were to look at our power supply here, a total of 2.4 coulombs per second is leaving that battery and heading for the external circuit. If we have two pathways that are equally likely, so in other words they have the same resistance, then that current will split equally when it reaches the split in the circuit. So the current through resistor 1 and the current through resistor 2 are both simply equal to the 2.4 amps divided by 2. And so both of them then are equal to 1.2 amps. And of course that means that we'll have a total sum of 2.4 amps for the entire circuit. The last piece of information is the voltage across each resistor. And this is kind of more of a known fact for parallel. It's not really a calculation. In the case of a parallel circuit, each resistor has a direct connection to the positive and negative terminals. So in other words, if we look at this resistor here, it's directly connected to the terminals. There's no other resistors in the way. The same thing is true for this resistor over here. So both resistors get to take advantage of the full voltage of the battery. So that means that both voltage 1 and voltage 2 are equal to the total voltage amount, which again is 120 volts. Hello again. This time Sioux Falls physics teachers looking in more detail at parallel circuits. Two resistors of 8 and 12 ohms are connected in parallel with a potential difference of 6 volts. Calculate the current through each resistor. Now again, it doesn't specifically tell us that we need to do this, but it's probably a good idea to kind of go ahead and draw out a real quick circuit diagram of this situation. And notice that again we would have 12 ohms and 8 ohms as our resistors, 6 volts as the value for the battery. In this case, it specifically says calculate the current through each resistor. So one of our habits with a complex circuit is to find the equivalent resistance first. In this case, we actually don't really need to do that. We can actually go straight to our equation of V equals IR. We'll make the 8 ohm resistor R1. And the first thing we're going to do is apply Ohm's law directly to that first resistor. Notice then that voltage 1 would be the same as the total voltage of the battery. So even though we would say that our 6 volts is the total for the circuit, resistor 1 gets to take advantage of that full 6 volts, so we can simply plug that in as the voltage for the first resistor. Plugging in 8 ohms, we will find then that our current through the 8 ohm resistor is 0.75 amps. Next, we can repeat exactly the same thing Applying Ohm's law, in this case, simply to the second resistor, which is the 12 ohm resistor. Again, the 12 ohm resistor also gets to take advantage of the 6 volts. And that will be 12 ohms total as our resistance. Calculating that out, we find that I2 is equal to 0.5 amps. So we have a total of 0.5 amps through the 12 ohm resistor, 0.75 amps through the 8 ohm resistor, and that satisfies our question. Notice that if we wanted to, we could calculate equivalent amounts for the entire circuit, and that would give us a way to double check. But in this case, simply to answer the question, we can give the two currents individually. Hi everyone, Sioux Falls physics teachers looking at series circuits. 3 resistors are connected in series with 12 volts. Draw a circuit diagram and find the equivalent resistance and current. First thing we want to do is draw our circuit diagram, and notice that since they are in series, series indicates that the 3 resistors then are all in a line. So we would start with 1, continue through the second, continue through the third. Our labels for those, we have 33, 45, and 86 ohms connected to 12 volts. Next, we would find our equivalent resistance. And remember that when in series, the resistance equivalent, or the series amount, is simply the 3 added together. So this time we will have 33 ohms, 45 ohms, and 86 ohms added together for a total equivalent resistance of 164 ohms. The last portion of this question asks for the total current in the circuit. So we can take Ohm's law of V equals IR and apply it to the total amounts for the circuit. This would be 12 volts for the potential difference. Current is our unknown, and we've just calculated our total resistance at 164 ohms. And as expected, this would give us a very small amount of current, 0.073 amps, as our total amount for the circuit when the 3 resistors are connected in series. Hello again, Sioux Falls physics teachers looking more at series circuits, this time 2 identical resistors of 100 ohms. First, we are again asked to draw a circuit diagram. 2 resistors in series simply means that we need to make sure to connect them along the same path of the circuit. As far as labeling, they are equal at 100 ohms for the 2 resistance values and 120 volts for the potential difference. First, it says to determine the total current in the circuit and the voltage across each resistor. Before we do that, we will need the value for the equivalent resistance. And again, because we are working in series, we are simply adding the 2 together. So 100 plus 100 gives us an equivalent resistance of 200 ohms. Then we can use Ohm's law, V equals IR, applied to the entire circuit to calculate the current. We again have 120 volts. Our resistance was just calculated as the total of 200 ohms. And as expected, we would have a very small equivalent current then of 0.6 amps. So that then is the answer to the total current in the circuit. Notice that it doesn't specifically ask this for this question, but that 0.6 amps that is leaving the power source is going to be traveling through both of our resistors along its pathway. So if we were asked about each of them individually, both of the resistors also get that current amount of 0.6 amps. The next part of this question then is to determine the voltage across each individual resistor. Again, one of the keys for series is that the voltage is shared. So voltage 1 and voltage 2 will be only a portion of the 120 volts. Now again, in future problems, we can look in more detail at how we would calculate this for unequal resistors. But because we have equal resistors in this case, we can find the voltage applied to each simply by splitting our total voltage in half. So voltage 1 and voltage 2, each one of those resistors would get the benefit of 60 volts rather than 120. Hello from your Sioux Falls physics teachers, looking more today at series circuits, this time with two resistors of unequal amounts, 8 ohms and 12 ohms. We are to calculate the current through and potential difference across each resistor. So first of all, and again, the problem doesn't specifically include this, but it's not a bad idea to add in a circuit diagram just to refer back to later. Again, we have 8 ohms and 12 ohms as our resistance values, 6 volts for the voltage. First, we need to calculate the current through each resistor. Well, it doesn't tell us to do this, but before we can determine current, we need to determine the overall resistance. So in the series circuit, those are simply added together. So we have 8 ohms and 12 ohms for a total of 20 ohms for the circuit. Then we can apply Ohm's law to the entire circuit with our 6 volts as the voltage and our 20 ohms as the resistance, and calculate the equivalent current, which is 0.3 amps. Now notice that that would be then 0.3 amps of current, or 0.3 coulombs per second, leaving the battery. In a series circuit, that charge has only one possible path, and that includes both resistors. So when we have found the equivalent amount of current in a series circuit, that is then equal to the individual currents as well. So 0.3 amps being the total for the circuit is also equal to the total current through resistor 1 and the total current through resistor 2. So we've already calculated the current through each resistor. Now we want to calculate the potential difference across each resistor. And remember that for a series circuit, we may have 6 volts as our total for the circuit, but that voltage will be shared. So if we have R1 here as 8 ohms and R2 as 12 ohms, we want to figure out how many volts for each. Now in this case, 8 and 12 are kind of a nice ratio. We probably could do this simply through using ratios, but for more complicated amounts, we're going to want to see how to do that with an equation. So what we will be doing is applying Ohm's law to each of the individual resistors. Okay, so we have the current amount at 0.3 amps. That's the total for the circuit, but it's also the amount through resistor 1. We'll use 8 ohms as our value for resistance 1 and we see that we get 2.4 volts as the voltage that is used across that resistor. So if we think about this volts as being an energy amount, 2.4 volts of that is used in the first resistor in the series path. We can then repeat the calculations for the second resistor to figure out the second voltage. And to save a little time, I've worked that out ahead of time. We end up with 3.6 volts as our total for resistor 2. So again, if we think about this in terms of energy, as charge leaves the battery, it possesses 6 volts or 6 joules per coulomb of energy. As it follows the path through the circuit, upon encountering the first resistor, it needs to use 2.4 joules per coulomb of energy there. As it continues on to the second resistor, and notice that that's a higher resistance, so it is a more difficult part of the path. There it uses 3.6 volts, and of course if we add those together, we would see that we end up with a total of 6 volts used for the entire circuit.